G'day nerds. So let's talk about covalent bonds. Now, by the end of this, we really want to be able to determine when a covalent bond is going to occur, as well as describe its nature. Also, we want to be able to represent it using a Lewis dot structure diagram. So, here's your vocab for the lesson. I want you to pause the video, write this down, so you've got it to refer back to later on as we move forward. Now, what is a covalent bond? Here we have some excellent diagrams of covalent bonds. The only electrons that we can see on this diagram are the valence electrons. Okay, that's important. Now the valence electrons are there to show us what's happening. And the one thing you'll notice is that we've got a lot of elements, or a lot of combining elements here, which are sharing electrons. And the reason they share electrons is to make up that stable octet. So atoms with Pauling scale differentials of less than 2 will form covalent bonds. In other words, the differential is not enough that they will be able to strip electrons away from the other. What's going to happen is they will share the electrons to make that stable outer shell, stable octet. These are known as molecular bonds. And when we talk about molecules, we're really only talking about covalently bonded stuff or the occasional monoatomic element. But generally, we're talking about covalently bonded things when we talk about molecules. So covalent compounds, they exist as molecules where the chemical formula represents the molecule. That's what we call covalent molecules. We can also exist as covalent networks, and these will exist as a lattice. That should be down there. Because we're chemists, we can write things properly. When we talk about a covalent network, that's very similar to an ionic network, an ionic lattice, where the formula we see, it just represents the lowest possible ratio of different elements in that crystal lattice. So, actually I want to go back. So yeah, we just see here that the bonds are being shared, the electrons are being shared, and we can draw them in different ways. Here we can see we've got like essentially Lewis dot structures. We can write it as a molecule, and so forth. Just there are various ways to represent this. So anyway, polarity of covalent bonds. So we've got nonpolar covalent bonds. They occur when there's an electronegative differential of less than 0.5 and on the Pauling scale. And this means that they just share equally. And so when we look at it, you actually see an electron cloud that looks like this between the two atoms in that molecule. And when we talk about covalent bonds, we're talking about you could have a molecule of 1,000 atoms, but we talk about each bond individually. We can have a polar covalent bond, which is where we see it now we've got an electronegative differential, and that's anywhere with a Pauling scale difference of 0.5 to 2. Beyond 2, it turns into an ionic bond and we strip them away. But when there's a larger electronegative difference, but not enough to make it an ionic one, we get a polar covalent, which means at this end here we have more negative charges than we do positive charges over here. And this looks like this, right? So this is water. This is one of the really common polar covalent compounds. In fact, it's the most common. It's just the one that we see everywhere. And we see the oxygen is very large. It's very electronegative. The hydrogen is not very electronegative at all. And this means the bonding pair it's formed in its sharing is stored around there. So we think of electrons as being free to roam essentially around the atom. But this one here, particularly just say if this one here is the one which comes from the hydrogen, it's not free to roam all the way around. It actually sticks locked in nice and tight, close to that oxygen, mostly. And because it's stuck in nice and tight close to that oxygen, it's why we end up with this shape here. And so yeah, that shape is the electron distribution. Anyway, so that's a polar covalent bond. Now, how do we represent these using Lewis dot structures? First, when we combine carbon, we burn carbon, that's the graphite in a pencil, with oxygen, we get carbon dioxide. And what we're actually seeing now, with the Lewis dot structure, we only draw the valence electrons, and if you're unsure, there's another video of mine that you can go and check out just a bit more detail on how this is done. Anyway, we draw the valence electrons for oxygen, the valence electrons for carbon, which is carbon has 4, oxygen has 6, this carbon here has 4, sorry, this carbon's still that carbon, this oxygen here has 6, and we see that now this carbon is using these two electrons from the oxygen and these two electrons from the oxygen to give it that sort of stable outer shell. Now, there are other ways around it. For example, we can go to carbon monoxide, and we can see that we've got that's from our oxygen, that's from our oxygen, and these are from our oxygens. So that's at 6, and here the carbon is providing one bonding pair, and its lone pair is out there separately. So we draw our lone pairs first when we draw our bonds, and then we draw the shared pairs as well. And here's water as well. Now, this is not Lewis dot structure, but it is one way we represent molecules, particularly when we move into organic chemistry. Again, I've got a video on how to draw these specifically with just a bit more detail. So I hope that made sense. If you have any questions, put them in the comments below. We'll get to you as quick as we can. Thank you for watching. And yeah, don't forget to subscribe so you can keep up with what we're doing. And we'll see you next time. Bye now.